Hello everyone. So let us continue to apply valence bond theory into predicting the structure of the molecule. So we'll start with the BeF2 molecule. So I hope you remember how we tried to use the VSEPR theory in order to find the structure of or the shape of the BeF2 molecule, and we found that BeF2 possesses a linear structure because it has two electron domains surrounding the central atom. So according to VSEPR theory, they should have a linear shape. Okay, so this was a more empirical approach because it considers only the empirical formula like Lewis structures in order to predict the structure of the molecule. So VSEPR doesn't talk anything about the atomic orbit. Now VBT, which we are trying to use in order to explain the structure of the BeF2, we are going to consider the valential atomic orbitals of beryllium and fluorine individually and try to find out which orbitals are going to overlap, leading to the formation of bonding in the beryllium fluoride. So if we look at the ground state electronic configuration of beryllium, we found that the electronic configuration is 1s2, 2s2, 2p orbital is completely empty because beryllium is 4 is the atomic number. So this is the electronic configuration. Now for fluorine atom, so this is the electronic ground state electronic configuration for fluorine atom. So if I just draw the in a box form, just the valence shell. So it is the 2s and this is the 2p. So if I fill the electrons, it would be something like this. Okay, so this is the electronic configuration. So I told you the overlap between the atomic orbitals is possible only if it is singly occupied. So if you look at the fluorine atom, one of the 2p subshell is singly filled. So there are two fluorine atoms. So each of the fluorine atom will use 2p orbitals to overlap. Okay. Now, when we look at the beryllium, it should also contain singly filled electrons in order to participate in bond formation. Okay. But when we look at the electronic configuration, it is 1s2, 2s2. So it is completely filled. There is no unpaired electron to form any bond. So in order for this beryllium to undergo any kind of bonding, we have to envision another electronic configuration, and that we refer to as the excited state electronic configuration of beryllium. So what we do here is we will try to excite one of the valence electron in the 2s orbital to empty 2p orbital. So when we do that, when we unpair and excite the electron to the 2p orbital, we get two unpaired electrons present on the 2s and the 2p orbital. So now beryllium can form two bonds, okay, and because there are two unpaired electrons, so it can form two bonds with the two fluorine atoms very easily. Now if you look at these orbitals that are actually overlapping in the case of the central atom, one of the overlap is happening between the 2s orbital and the 2p orbital of the fluorine of one of the fluorine atom, and the other overlap is happening between the 2p orbital of the beryllium and one of the 2p orbital of the other fluorine atom. So if there are two different kinds of orbital that are involved in bond formation when it comes to beryllium, then that should mean these two bonds are completely different. That means the bond length should be different and the nature of the bond should be different because they are completely formed with the overlap of different set of orbitals. So if we consider separately on beryllium atom, we have two sets of orbital. One is s, one is p. So this s will overlap with the p orbital of this fluorine, and this p of the beryllium will overlap with the p orbital of the fluorine atom. So they are completely two different bonds, but we know from experiment that these two bonds are equivalent. That means they have the same bond length. So if that need to be understood, we need to consider a slight variation in this fact, because if we consider 2s overlapping with the 2p, this kind of equivalent orbital isn't possible. So that means, that is what is written here, two different orbital type leading to unequal bonds, which is contradictory to BSEPR, because BSEPR predicts that the two bonds are equal, okay, they are equivalent. Okay. So how to solve this problem? Okay. So that problem is actually sorted out when Pauling introduced a concept of hybridization. So this particular concept was actually introduced by Pauling, because he introduced this concept of hybridization. So hybridization basically means mixing of the orbitals. So if you look at the central atom, there is one s orbital that is containing unpaired electron and one p orbital which is containing the unpaired electron. So Pauling suggested that there is a kind of mixing of the s and the p orbital, leading to two hybrid orbitals which are called as the two sp orbital. Why it is called sp orbital? Because it is mixing of one s and one p orbital. So when two atomic orbitals are mixing, it leads to two hybrid orbitals, and both are equivalent. Okay, both are equivalent and both are termed as the sp hybrid orbital. So when we superimpose these two hybrid orbitals, they would be directed at 180 degree to each other. Again, the concept of balloon that I talked about when we talked the VCPR theory. So here again, the orbitals would be trying to avoid any kind of repulsive interaction, so they would be as far as apart as possible. So the two hybrid orbital, two sp hybrid orbital would be directed on the at 180 degree to each other. So here there is the hybrid orbital. If you look at, there is one large lobe and one small lobe, one large lobe and one small lobe. So when we write the ultimate structure of the sp hybrid orbital that is formed as a result of mixing of one s and one p orbital, we only write the larger lobe. We usually do not represent the smaller lobes. So this is the hybrid orbital for the beryllium. So now beryllium is actually composed of two hybrid orbitals, which are basically the two sp hybrid orbitals of the beryllium atom. So each of the hybrid orbital is containing single electron, okay, and the fluorine will interact with its 2p orbital. So they will, the singly filled electrons will pair up, leading to the formation of chemical bonding. So the concept that was introduced by Lewis, that pairing up leads to the formation of a covalent bond, is very well explained now by taking into consideration the orbital overlap in the case of valence bond theory. So this is a very important breakthrough in understanding the structure of the BeF2 molecule. Moving on further, let us look at another example of sp hybridization. So if we look here, this is the example of acetylene. Acetylene is basically your ethyne molecule. So ethyne molecule, that means you have a triple bond present. So there is one sigma bond and there are two pi bonds that are present between the two carbon atoms. So if you are asked how many sigma bonds are present in this whole molecule, there are 3 sigma bonds. How many pi molecules? Pi bonding, there are 2 pi bonds present in the ethyne molecule, and this you might have already understood. Now let us try to understand the bonding here. Okay, so we have to consider each of the carbon atom, because this is kind of a central atom. So far you have been discussing only one central atom with the other atoms surrounding it. Here there are 2 central atoms, so each central atom would be considered individually. So let us consider one of the carbon atom. Whatever we consider for this carbon atom would be the same parameters for this particular carbon atom as well. So let us look at one of the carbon atom. So if we write the ground state electronic configuration, so this is the ground state electronic configuration of the carbon atom. So we find it is 2s2, 2p2. Okay, this is the ground state, and one of the 2p orbital is empty. So here this carbon is forming how many bonds? One bond with the hydrogen, another bond with the carbon. So it required two unpaired electrons, and here in the ground state we see exactly two unpaired electrons here. Okay, so you might say that, okay, then we do not have any problem. We can directly use these orbital in order to form bonds with the hydrogen and the carbon atom. But if we look here, this is 2px and 2py, and they are directed at 90 degree to each other. So if we use pure 2px and 2py orbital to form the bond angle between these two bonds should be 90 degree, because they are 90 degree to each other. So that is not the case. We know that this bond, these two bonds that are across this carbon is linear. Okay. So in order to understand that fact, what we do here is we will try to bring in the concept of hybridization. So hybridization usually involves a combination of s and p orbital. So for that, for combining the s orbital and making it to participate in bonding, we have to first excite this electron to the empty p orbital. When we do that, this is the excited state electronic configuration of the carbon. And what happens is that one of the so let me write one more structure, probably then you would clearly understand this particular thing. So the excited state electronic configuration is something like this. Okay, so this is 2s, 2px, 2py and 2pz. So this is the excited state electronic configuration. Now since there are two bonds that are formed, we required only two unpaired electrons. So we will do the hybridization of 1s and 1p orbital, leading to two hybrid orbital, each containing one electron, as we discussed in the table, the beryllium fluoride. So this is the hybrid of two hybrid orbitals of the carbon atom. Okay, and these are the two unhybridized p orbitals. So on each carbon atom, there are two sp hybrid orbital, which is kind of forming sigma bond with this carbon and this hydrogen. So the shape is linear. Now on each carbon atom, there are two unhybridized p orbital, which is not kind of hybridized with each other. So that means they actually overlap in a sideways fashion. So these can overlap sideways. Okay. So this sideways overlap lead to the formation of pi bonds. So since there are two unhybridized p orbital, there are two pi bonds that are possible in the case of ethyne molecule. Because in ethyne molecule, after hybridization, there are two hybridized sp orbital and two unhybridized p orbital. And that is why we have two pi bonds possible in the case of acetylene. Okay, so that is how valence bond theory clearly explained the formation of sigma bonds and pi bonds in the case of ethene molecule, and it clearly explained the overlap and the formation of bonds in terms of atomic orbital. So I hope you can clearly understand the use of valence bond theory in explaining the structure of not only BeF2 but also of acetylene, where we saw the hybridization of 1s and 1p orbital leading to the formation of two sp hybrid orbitals, and the shape of it is simply two large lobes. Okay, so we will discuss in the coming video more applications of this valence bond theory in explaining the structure of the molecules. Until then, have a nice day.